So jumping in, leading our webinar today is PointClear Solutions Vice President of Technical Services, Michael Atkins. A little bit about Michael. Michael joined PointClear Solutions in 2017, and he's responsible for overseeing all aspects of the company's technical services functions, including management of our team of architects and engineers. Before joining PointClear, Michael spent several years with Change Healthcare, where he served as Director of Applications Development in the Engagement Solutions Division. Prior to this, Michael was a Director of Healthcare Clinical Solutions Development with Walgreens. Michael holds a degree in Computer Science and Accounting from Mississippi State University, and he is based out of PointClear's Nashville office. With that, I'll turn it over to Michael. Welcome, Michael.
So thank you, Laura. Thank you, everybody, for making time for this. We're going to jump right in. And so today we're going to hopefully give some definition to a phrase that you have heard probably in the marketplace. We're going to define what it is when we say machine learning. What is it that we're actually talking about? We're going to give some goals and examples of machine learning in everyday life. We'll be looking then specifically at care, looking at the current healthcare marketplace with respect to machine learning, some of the challenges there, and then what's likely ahead of us in the next decade. And then hopefully all of that content excites you, and you want to jump right in. So we're going to lay out how should you proceed, whether you're planning on doing this in the next year or maybe 5 years from now. There are still things you can do today to make that easier for you. And then at the end, we'll have time for your questions, and so send those on through as we go through this. Starting with a definition, and really the entire presentation will kind of flesh out more definition, but at a 30,000-foot view, machine learning is an attempt to extract knowledge from data. Piles of data, and we look for patterns, and that data can be data as you traditionally think of it. It can be completely unstructured. It can be images, audio, video, any of the media you might be able to record and feed into a machine constitutes data in a machine learning context. So let's take a step back, because while there's been a lot of innovation in recent years and months, even a lot of the underlying thoughts and even some of the underlying technology is really not that new. So Alan Turing, after World War II, he and his associates at Bletchley Park had just cracked the Enigma machine and helped to win World War II. And he was really one of the first kind of widely recognized scientists to even talk about machines potentially having intelligence. He created kind of what's known as the Turing test, which says if you're conversing with a machine and you can't tell whether it's a machine or a human you're conversing with, there has to be some aspect of intelligence there. And I'm not going to go through each of these bullets, but you can see that, and these certainly don't represent an exhaustive history of machine learning, but you can see that progress, was decades and years in the making initially. You fast forward 40 years, and that convolutional neural network, that advancement is still the technology that underlies most computer vision machine learning models even today. So think recognition or depositing a check with your phone, that image recognition portion is likely riding on top of that technology. And then fast forward another 10 years and to something that a lot of us remember is IBM's Deep Blue, and the first time a machine had beat a world champion chess player in a tournament setting. At that time, 25% of American households have internet access. So that just gives a little context there. And that all of that leads up to 20. So in the last 20 years, the web has happened. we've seen hardware and software make leaps and bounds in terms of the capabilities, the processing power, specifically in graphics processing, which we leverage because there's a lot of advanced math in machine learning, and so the power to do matrix manipulation is often found in graphics hardware. Obviously, you know, the cloud gave rise to our ability to collect all of this data. We need massive amounts of data, and the cloud gave us a place to put it, and then gave us the ability to compute on that data, kind of in a pay-as-you-go fashion. You know, the advances in machine learning itself, you know, machines started beating us at all the games. You know, Jeopardy, we all remember Watson kind of showing up and winning Jeopardy. It's beat human champions at Go, and even games like Texas Hold'em, where you know there's information that's secret among the players. It's really kind of instead of decades and even years in advancements, you know, you're likely to in 2017, 2018 see really major advancements take months, or in some cases, you know, weeks. You know, there are things that have been talked about even or written about even this month in October that are just mind-blowing. So the pace of advancement is picking up, but the ideas are still built on a foundation that's not all that new. In some ways, we can think of machine learning as kind of backwards software engineering. You know, in traditional software products, we define the rules, right? We lay out how we want the software to behave, and then we put data in the system, and we get a result out. You can think of machine learning as taking all that data and giving some result information in order for the product to be the rules themselves, the patterns within the data, you know, power to make decisions and predictions, all of those things coming out. That is what we get when we build a machine learning model. So a machine learning product, you know, project, the output of that is going to be software that we then use as if it was a system we had built traditionally. We then, you know, put in new data, and we get predictions, decisions, actions to take. Obviously, the success of any machine learning model depends on the data it was used that was used to train it. So we need lots of it, and we need it to be consistent, and we need, you know, a lot of the attributes of data that we think of in traditional ETL projects. We need those characteristics to exist. You know, one area that gives us concern, and machine learning is rife with this, right? On the one hand, there's excitement, and on the other hand, there's kind of concern or a little bit of trepidation. What's actually going on here? And part of that is because once we get this machine learning model, it's not always easy to understand how the model produces the prediction or decision or action it does. You know, you may have trained your model on thousands or tens of thousands of variables, and then at the end you get, you know, some decision out the other end, and it's not always easy or even possible to trace back through and figure out exactly why that data led to that decision, and so that causes concern occasionally. We're going to go through some categories of machine learning just to give you, you know, kind of that next level of depth here. This is certainly not the only way to categorize machine learning models. You could talk about algorithms and hardware and all of those things, but we're kind of going to take a pragmatic approach. We're going to talk about, I guess, a goals-based approach to categorizing machine learning. So we're going to talk about three categories: supervised learning, and reinforcement learning. Supervised learning basically takes labeled data, so data that is accompanied with some label based on what you're trying to do, and then we train the model with you know, a portion of that data, and then we test the model with the other portion of that data to see if the predictions that the model produces line up with the labels that we put on the data. So we measure success here in kind of how well the machine matches our the labels in our test data. So to put some skin on the bones here, you can imagine that this is a patient record database, an EHR, and what we want to do is we want to build a model that predicts diabetes diagnosis, for example. So we'll take as many patient records as we can get our hands on, and we'll label them. This patient was diagnosed with diabetes. This wasn't. This wasn't, until all of those records have one of those labels. Then we'll take maybe 80% of that and we'll train our machine. We'll feed those through, and the machine will look at the data and read the label and find the patterns in the data that correspond to that label. And then we'll take the other 20% and we'll test our model, and we'll say, okay, if you found the patterns, now I'm going to feed this data through, and you tell me what label should apply. And that's how we'll gauge how successful we've been. And as always in machine learning, we're not looking for perfection. We are looking for a prediction accuracy that's at least as good as humans doing the same thing. So if I gave a human this patient record, how many times would they arrive at the correct diabetes diagnosis? And so that's kind of the standard that we're looking for here. Then there's unsupervised learning, where we just take the data and we don't necessarily go through the effort of labeling everything, but what we're looking for is the machine to break down the records into clusters of similar records. And so we can start and we could say, I want to conduct a marketing campaign that's going to target a dozen different segments of consumers, and here a pile of consumer behavior data, purchasing, browsing, app usage, whatever that data is, and I want to target a dozen different categories of consumers. So I might run that data through here, and I might say, okay, machine, break this down into a dozen similarly grouped sets of consumers so that I can target my campaigns appropriately. That's what unsupervised learning is typically results in, is those clusters. Then there's reinforcement learning, and this is a fun one. Instead of taking data and labeling it, or even taking it as is, we operate on state and action data. So you can think of data in a time sequence, and then we apply a reward function. We say we want you to reach this state, and here's a bunch of existing state and action information, and so tell me what action I should take. And where you see this is, and the reason I say it's kind of the fun area, is that this is used in kind of games learning, right? You might be wanting to teach a machine how to play Super Mario Brothers, and you say, okay, if Mario is standing under a block and he jumps, that's the action, then the result is, the star comes out and you get lots of points or whatever. And the goal function is, we want you to reach the end of the stage. And so, given enough of those state and action kind of points, later the machine could play the game and realize, I'm in this state, and I know if I jump, I'm going to move toward my goal. So that's where a lot of reinforcement learning experimentation is taking place now, is in gaming. So you're already using machine learning daily in ways you may realize, and then in other ways you may not realize. I wanted to stop here. Andrew Ng was a professor at Stanford University very recently, one of the founders of Coursera, which is an online, a massively online course site, and now he's chief scientist at Baidu, and he said artificial intelligence is the new electricity, and what he means there is, just like the electrification of the country and the world impacted every industry, no industry was left untouched by electricity. Likewise, he's saying, artificial intelligence is going to have that same kind of global reach. There's not a human endeavor or enterprise that isn't going to be impacted in some way by artificial intelligence and machine learning. And so I just wanted to give a little context there, because that quote may not make sense otherwise. So if we're going to do this work, if we're going to, you know, bring all this data together and build this model, what are some of the goals we might have in mind, kind of at a high level? Well, certainly we want to provide actionable knowledge, not simply static analysis. I wouldn't build a machine learning model to calculate an average of some data. There are lots of good ways to do that already exist, and certainly you don't need a machine learning model to do, you know, that kind of static analysis and just give you calculations over the data. What we get out of machine learning is a model, a set of rules represented mathematically that we can then use to feed new instances of data in and get out predictions, classifications, actions, recommendations, those types of things. So we're looking for actionable things here. In some cases, you're going to look to augment what humans are already doing in order to be more efficient. If you've got an Alexa at home and you've ever said, Alexa, play me some jazz, you know, that natural language processing that hears your voice and turns your words into an action is augmenting something you could have already done yourself. You could have gone and turned on some jazz music, but instead, you know, we're augmenting that. We're taking the need for you to focus your concentration on that task, and we're handing that to a machine. We want to provide accuracy at least as good as humans, and in a lot of cases, you know, as we mature and collect even more data, you know, models will exceed human capacity in many areas. And then we certainly want to enable us to do things with machines in areas that might be too dangerous or just flat out inaccessible to humans. You can imagine kind of deep space exploration being done by you know, a machine before we would send humans there. You might also imagine that, you know, drug delivery to a specific disease site where we might leverage a nanobot to, you know, with some intelligence to deliver that medicine, where, you know, a physician doing the same thing might be too risky to the patient, you know, might take too long to recover from something like that, and so, you know, having some intelligent machine do that might make more sense in those cases. Ways you're already using machine learning today, if you use a search engine or surf the web or tweet or post on Facebook, you are participating in certainly at least you know, advertisers' sense of machine learning. So you are in one or probably many of those clusters we talked about in that unsupervised learning, where your similarity to other shoppers is being you know, compiled, and ads targeted at people like you are, you know, ultimately going to be way more effective for advertisers. You click that button that labels an email as spam, and you tell, you know, Gmail or Hotmail or Outlook, this message is spam. What you've done is applied a label to that email, and that then goes into a supervised learning algorithm where, you know, along with emails that aren't spam, the machine is getting better and better and better at classifying those emails as either spam or not spam over time, and you're participating in that. Online check deposit. If you've ever taken a picture of a check and deposited it in your bank account, you know, you may have noticed that the app might tell you, hey, make sure you sign the back. Well, how do they know there's a signature there? Or there's a convolutional neural net looking at that image and determining whether a signature exists or not. And then ultimately where we want to get is, you know, one of the places we want to get is autonomous vehicles, you know, that self-driving car. You know, every Tesla on the road today is sharing data back to Tesla so that the model being built benefits every car on the road over time. So as humans take actions, you know, that video data, that audio data, that awareness that the car has is being shipped back to build a better and better model for how to drive. And again, no one's writing down or coding anywhere to describe to the machine how to drive. The machine is deriving that straight from the data. So let's bring it home to healthcare and see where we're at. So what's happening now? You may know that IBM Watson didn't go away after winning Jeopardy. IBM has been constantly evolving it, and now it plays a big role as a platform in healthcare. They formed some partnerships with EHR vendors, medical imaging vendors, things like that, and there's been a tremendous amount of success, specifically in radiology and pathology, parts of medicine that are very image intensive. Machines are very good at image analysis now. So you might have on one end of the spectrum what's called computer-aided detection, where a machine might just see an anomaly in an image and alert a medical professional, hey, there's something here. The other end of the spectrum is computer-aided diagnosis, where beyond just detecting something strange in an image, a machine might reach a diagnosis and say, I have detected this type of cancer or this type of lesion, in this image. And so, what we're up against now is that the regulatory environment has to get comfortable with, machine learning, its upside and its potential downside, which is that inability to examine what's really going on inside. So the regulatory environment is struggling a little bit to keep pace. This year, the FDA did approve a system called Arteries to actually diagnose some heart conditions. And in doing so, the FDA set up the standard that it had to be provably better at reaching those than humans given the same kind of imaging data. And so they crossed that threshold, they got FDA approval, and now that is a machine learning model that's actually doing diagnosis work in healthcare today. Obviously, there's considerable challenges still ahead of us in reaching, all of the goals you can imagine for this kind of technology in healthcare. There's fear. There's a fear of automation. If we can rely on machine to augment what we're already doing, at what point does augmentation just become replacement? The machine's now as good at doing it as we were, so why would we be necessary? So there's that fear that we're all going to be automated out of work or out of business. Then there's the fear of the black box, and that's that notion that I don't always trust the decisions because I can't look inside and see how the machine reached that particular decision. And so, we've got to come up with ways of validating that don't rely on just line-by-line analysis, a strict set of requirements being written, but rather, provable abilities to surpass human capacity in those cases. We need lots of data, and right now in healthcare, as you know, sharing data, standardizing data, all of those things are really enormous challenges. Privacy regulation prevents sharing certain types of data that would help, at an industry level, us to build models that do better jobs than we can do. So, we're up against some regulatory, not just regulatory, but even ethical concerns. Like when safety and privacy collide, if for example, you had genetic information from a set of parents that you knew introduced risk to their offspring, there's a safety concern for the offspring, but a privacy concern for the parents. And those aren't just easily set aside questions. They're very real and very prescient today. As concerning as all of those challenges are, I hope that you leave this webinar with a sense of excitement. I mean, we all either are or will be consumers of healthcare as well, and the things that are going to happen in the next decade, quite frankly, excite me enormously. I'm looking forward to the day when accuracy, when speed, when my ability to get from some measurements about myself, maybe even some genetic data, can give me some actionable outcomes way quicker than it can today. So what's next? Computer diagnosis is going to be a reality. It's a matter of time. It's going to be faster than humans. It's going to be more accurate than humans, simply because it's not a disparagement against humans, but our capacity to hold the number of variables required in our heads at all times just just isn't there. We make mistakes. We are limited in our capacity, and soon, machine learning models are simply going to be able to reason about more things at once than we can. Outcomes prediction, again, very, very tailored, personalized awareness of all the factors around your healthcare, your behavior history, your family history, your genetic situation, your socioeconomic situation, population health concerns, all of those things. Our ability to synthesize drugs tailored to a particular patient's context, again, genetic, behavioral, all of those things are going to explode in the next decade. We're going to have capabilities that seem like science fiction today very, very soon. So, while we're all in healthcare delivery and some of this makes us very nervous, I hope it doesn't stop there, and I hope you see that humanity and is going to really thrive when we get some of these capabilities out into the healthcare marketplace. So let's say you got really excited up to this point, and you're like, I want to start this tomorrow. What can I do to either get going or to prepare to get going at some point in the future? And the truth is maybe less exciting than you would hope it would be. As novel and interesting as all the math and the algorithms and the software around this stuff, the tools that are available, it really boils down to having the data available. So it really is data. Much of your time and energy in a machine learning project is going to be spent collecting, assimilating, and then normalizing and standardizing data. It's going to feel like a traditional ETL project in many respects. So you're going to need to enhance potentially data consistency across multiple systems. I caution there, though, be careful, because when in doubt, do less here, because the risk you run is if you make the data too clean, you'll build a model that works perfectly well against your nice, pristine data, but then as real-world data comes in after the fact, it falls over and accuracy plummets. So you want to compile the data and get it consistent, but you don't want to do too much. You don't want to be enriching the data or trying to outsmart the machine and teach it things that aren't going to be present in real-world data. Or again, your accuracy will be really high when you're training, and then really low in real-world applications. Understand that your EHR is going to be certainly a central figure in your data sphere, but not all the data you need is going to be there. You may have some kind of outcomes, survey information that you need to pull in from other systems. You may have, patient demographic data that might live in other systems, and you're going to need to based on your goals for the project and the types of predictions you're looking to make, you're going to need to pull all that data together. So just be aware that need's going to exist. Sometimes you might need to supplement data because either you just don't have enough as a single practitioner or even a single hospital chain. You may not have enough data on your own. There are public data sets that are available. Amazon hosts gigs and gigs and gigs of publicly accessible data sets. Some are healthcare related or might be relevant. Many won't be, but take advantage of them as they pertain to your particular use case and goals. Again, avoid the temptation to filter the data or try to massage it into some shape that you think is going to help the machine, because while the truth is you might help it in that training scenario, again, your accuracy will drop if the real world data it sees afterward is different. So again, less is more in that realm. And by all means, even if you don't see yourself undertaking a real machine learning project, and even in the next 4 to 5 years or decade, or maybe you don't imagine it ever, go ahead and take some steps now that are going to reduce that friction should your timeline change or your ideas change. Begin working on those things. We're going to give you some concrete steps in a couple slides, but don't wait until a month before you're ready to start your machine learning project in earnest to begin working on your data. And then iterate. Iterating in traditional software is a little scary, you know, because there are certain assumptions and decisions that if I change them down the road, you know, there's a huge impact, and we're going to have to go and rewrite entire portions of the system to accommodate that change. Usually, iteration in machine learning just means pulling in more data, either, you know, more variables, you know, more types of data, or just more records. And so, you know, iterating in this world shouldn't be, in most cases, nearly as scary as that word can be in traditional software. So don't be afraid to start small, build a model, look at the accuracy, and then just go get more data. Find sources, you know, work with industry groups, pull in those public data sets, and go from there. And the point of this slide in its entirety is don't get married to tools. The tools that are most widely used today are only a couple of years old, and the pace of change in this space in particular is really too high to even attach. So you know, I'll go through a couple of them, but the last bullet is really most prescient. This can be very overwhelming. Just pick one that feels comfortable for you today and go with it, and just assume that you're going to have to evolve your tools over time. TensorFlow is that one that I mentioned that's probably the most widely used in kind of the generic sphere of machine learning today. It was just open source by Google a couple of years ago, so it's less than 3 years old. Cafe 2, open source by Facebook this year. Microsoft's toolkit is, you know, about a year old now. And then, you know, there's even stuff happening in this month. AWS and Microsoft partnered to release an API set called Gluon. Their goal is to make things more approachable for developers. So, yeah, again, the pace here is really rapid. Lots of changes happening on a week-to-week basis even. So pick a tool, just assume it's going to have to change. Again, most of your energy is going to be on the data anyway. And here's some kind of concrete takeaways, right? What should we be doing today? Well, certainly, as you're making architecture and infrastructure decisions today, keep data in mind. You know, we want to be able to move data between systems. We want to be able to aggregate that data. We want to be able to pull it together and feed it into machines. And then to that second point, we want to be able to do that securely. So as you're, you know, thinking about privacy, thinking about security, you know, there's that balance between having access to the data and yet maintaining the security of the data. So keep both of those in mind, but certainly build today so that you're not having to lay these infrastructure pieces at the same time that your team is really excited about moving into machine learning. Realize that you're going to have to span systems, and in cases, you know, all the data you have available in-house won't be enough. You'll need to pull in external data sets. So factor in that ETL design. You know, what is a good process for you and your business with the data you've got available to approach this in the future. Standardize. You know, pick a taxonomy, SNOMED, LOINC. Pick something that you're going to apply across your systems, so when you do begin to aggregate, you're not having to do a bunch of you know, matrices to figure out that this code in this system means the same as this code in this system. Go ahead and begin standardization today, and then really look outside yourself and advocate in the community, in the regulatory environment. You know, have a voice. You're not, if you're watching this webinar, you are not so far behind that you are you know, out of that conversation, that you can't have a meaningful place at that table. These ethical questions, these data sharing questions, these security and privacy questions, these safety questions are still very, very new and very, very prescient. So again, join industry groups, you know, join consortia, you know, work with regulators, make your voice heard in this space, because you know, for this to benefit humanity, for this to be something where we all arrive at a destination together. Sure, we're all running enterprises. We all need to be successful individually, but at some level, we need this data to be accessible universally in order for the true benefit to be realized. So with that, I really appreciate your time and attention this morning. Thank you for making time, and we've got quite a bit of time for some questions and answers. Hopefully this has led you to have some, and with that I'm going to turn it back over to Laura.
Thank you, Michael. And to our audience today, as you know, we've been experiencing some technical issues throughout this presentation. Thank you for hanging in with us. We do have several questions from the audience, Michael. So the first question, what should I be thinking about in terms of team transition as my company jumps into machine learning?
That's a great question. So first of all, that mixture of kind of fear and excitement exists at every level. It exists at a global level, humanity. It exists at an enterprise level. We're excited and yet we're fearful, and it certainly exists at a team level. What does machine learning? What does it mean to make this shift at a team level? And so, first, I would encourage be as open with your teams as possible. Make sure they know what your goals are. Make sure that to the extent possible, you involve them in tool selection, tool evaluation. Let them tell you where your data is, where data might be in your enterprise that's either legacy and forgotten about, or is just so hidden so deeply that it might not be readily available to you. Look to them for guidance there, and then certainly take advantage of education opportunities. There are, I mentioned Coursera, Andrew Ng's project. There are plenty of online resources, free and pay for tools. Udemy has a great course on TensorFlow. Make education part of that culture, because again, the pace of change is so rapid that there's time. There's time to get everyone up to speed and to really involve the team in goal setting and tool evaluation. So that's what I would encourage there.
Great. Our second question, do machine learning applications require massive computing power?
The best answer to that is hopefully, because what we're doing is we're processing large amounts of data, and so our goal is to parallelize and distribute that work out as widely as possible. But hopefully we have so much data that even then it takes a considerable amount of time, because accuracy will only improve as we provide more and more data to the model. So you certainly can build a desktop proof of concept of machine learning that runs on your machine and will run in minutes on very small data sets, and those are fun and certainly educational. But at scale, the goal is we really want and cloud computing, Amazon, AWS, and I know Microsoft are both building platforms for this, but certainly make that available at a pay by the SIP. But yes, we're hoping that we have enough data that it takes considerable compute power.
Okay, great, thank you. Another question, how does one measure that the machine is actually learning and applying those learnings?
So the best way is by testing against real world data, right? And again, if we know that humans are 90% successful at applying this diagnosis when they see this patient record, if our machine is also reaching 90+% accuracy, we can say that we're at least as good as humans. If over time our model begins to be less accurate, perhaps the data that's coming in is changing in some way, and we need to then go back and retrain our model on more recent data. So really, it's measuring the accuracy of the predictions and then setting that standard of human level accuracy is the best way to know that the machine's doing the right thing.
Great. And our last question, when designing systems based on machine learning, how can one best deal with tail events, i.e. black swans rarely, if ever, seen in the training data? How can we anticipate how a machine learning system will respond to the black swan?
And that's fantastic. And you know, the reality is that the machine relies on patterns that it sees in the data, and outliers, quite frankly, are going to continue to be outliers. The output of, let's say, a classification machine learning, where we're looking for a diagnosis, is likely not to be a single value. You know, this person has this condition. It's likely to be a set of probabilities. You know, it's 80% likely this person has diabetes. It's 20% likely they instead have, you know, chronic heart failure, and so or congenital heart failure. It takes into account that the certainty is certainly moderated when outlying data comes through, right? You would expect certainty to be lower in some of those cases. But you're right, and the flip side of that is it's very easy to create data that fools even the most recent machine learning algorithms. You can create an image that looks like that a human would classify, in one famous example, as a school bus, and add enough noise to it that the machine classifies it as an ostrich. So it's very easy to there are still some edge cases here, right? The outlier edge case, and then a malicious actor. It's very easy to create data that fools most machine learning algorithms today. So what we're looking for is patterns, and where those patterns fail, we still need the old style rules to help us muddle through that data.
Okay, I know I said that was our last question. We've had one more come in, so I'm going to go ahead and throw that one out there. Is machine learning expensive to implement?
Again, most of your time, energy, effort, and therefore expense is going to be in collecting and standardizing data. So it's, you know, I can really tightly correlate it to you know, a traditional ETL project. So you can imagine that the effort to aggregate and sanitize and you know, give consistency to data is going to be on par with that. The actual construction of the model, you know, again, you're going to need some education, you're going to need some basic introduction to the tool of your choice, but beyond that, you know, building the model itself isn't all that complex, and there are even tools that are being written about as recently as last week, where there are machine learning systems now whose output is a machine learning system. And so AutoML is a Google example. They've got one now where you basically give it your data and it decides what the best machine learning model would be. And so literally the only work in that case would be, or nearly the only work, would be collecting all the data. So if you've run an ETL project before, you can imagine that those aren't easy and cheap and free, but certainly that's going to be where the bulk of the cost comes from.
Fantastic. So those really are all of our questions. Michael, again, thank you so very much. And thank you to all of our listeners today for joining us. As a reminder, we'll be sharing a recording of today's webinar via email within the next day or so, so keep your eyes on those inboxes. And as always, if you'd like to learn more about PointClear Solutions and our consulting services, you can find us on the internet at pointclearsolutions.com. Thank you so very much.